this computer. Good. So now we are recording satellites in circular orbit. And let me get my illustrations as well. Universal gravitation right in here. Law of universal gravitation. Let's see. Okay, so recall whenever you have two masses, you have to memorize that equation because it's a law of physics, okay? There are 4 laws so far, right? 3 laws of motion, the law of universal gravitation, all of them attributed to Isaac Newton. So if you have two masses, one nearby the other, separated by a distance d, they exert a force, attractive force, given by this equation here. Big G is given by that very small number and that you saw before, and big DG is not the same as the acceleration of gravity. I want to emphasize that big G is not the same as the acceleration of gravity. It's possible to prove that that this type of force allows for 4 types of motion. One of them is the uniform circular motion. Okay? Possible to prove that this type of force, we cannot prove that here because it requires more advanced mass, that this type of force allows for 4 types of motion. Okay? 1, uniform circular motion, okay, UCM. 2, elliptical motion, parabolic motion, and hyperbolic motion, hyperbolic path, okay, or path. Hyperbolic motion or path, uniform circular motion or circular path, elliptical motion or an elliptical path, parabolic motion or a parabolic path, hyperbolic motion or hyperbolic paths. If you're following the news, we have an interstellar visitor right now that's in the solar system. Have you heard of that? It's the 3rd interstellar visitor that we have ever detected. The first one was the Oumuamua, no? So difficult to mention the name of the interstellar visitors. Here you go, interstellar visitors to the solar system. There were only 3 have been detected so far. And the latest one is the 3I Atlas. 3 stands for the 3rd visitor, I stands for interstellar, and Atlas was the system that detected the visitor recently. And why am I saying that? The reason I'm saying that is that the path of this visitor, of this interstellar object, is a hyperbolic path. Astronomers, when they detected this comet, right? They think it's a comet. Interstellar interlope is a comet resembling those in our solar system. Oh, well, that's the 2nd interstellar object. What about the 3rd? See, Oumuamua. Okay, Oumuamua was the first one that we detected. Interstellar visitors to our solar system. I want to see the list. Wikipedia has an article on that. Oh gosh. Interstellar interloper. Blah, blah, blah. 3 interstellar. Oh gosh. 3 interstellar visitors to our solar system have been discovered. The first one was Oumuamua. in 2017. Okay, it was a very elongated object. It was discovered very late in its visit to the solar system, so you couldn't get much of information from it. And we had the Borisov in 2019, and now we have the 3I Atlas in 2025. How do they know those three objects were interstellar visitors? Okay, the astronomers knew that they were interstellar visitors because they could calculate their orbit, and they found out that their orbit was either a parabolic one or a hyperbolic one. And they did that using Newton's law of universal gravitation. Okay, here you go. Oumuamua discovered 2000. It was the first interstellar object confirmed to be traveling through our solar system. It was described as cigar-shaped and was tracked for about 80 days only. Borisov, the 2I Borisov again, second interstellar object visiting the solar system, found in 2019. This object was identified as a comet, making it the second and the first confirmed interstellar comet. And then the Atlas is the third confirmed interstellar object. It was quickly confirmed to be a comet. And some evidence suggests it could be one of the oldest comets ever observed. So those guys were traveling through the interstellar medium, and one day they came close to the sun, okay? They go up hyperbolic orbits, okay? See that? Each object is traveling too fast to be gravitationally captured by the sun. They will pass through the inner solar system and they exit back into interstellar space. Because they are traveling so fast, because they have so much energy, the sun cannot capture them. Unless we manage it to somehow maneuver those objects, we would be able to put them in orbit around the sun. Okay? Some estimates suggest that 3I Atlas could be billions of years old, potentially older than our own solar system itself, making it a very ancient and pristine object. Okay, mission preparation due to their transient nature, there is no time to launch a dedicated mission, unfortunately, to intercept objects like 3I Atlas. However, future missions, such as the European Space Agency Comet Interceptor, are being designed to be ready for future interstellar visitors. So next time we'll be ready to intercept them. This 3I Atlas has a very strange orbit because it's very close to the orbital plane of the planets, okay? The likelihood that something like that could happen or could occur for an interstellar object is a very small, it's less than 1%, it's 0.1, 0.2%. That's the likelihood. And because of this very small likelihood, many people are claiming that this interstellar object could be a spaceship from an alien civilization, okay? But so far, there is no evidence for that. Most likely it is a comet. It would be great, right? If it were an alien spaceship that would be visiting. But so far, all evidence indicates that it is a natural object, despite its very low likelihood that has an orbit that's very close to the orbital plane of the planets. It's passing close to Mars and it's also passing close to Jupiter, but not close to Earth. Okay, it's gonna be. That's why I want to talk about that, because the topic, right? Here you go. Interstellar objects are either have a hyperbolic motion, a hyperbolic path, or you have a parabolic path. Planets in the solar system and satellites, they have elliptical motion, which is a flattened circle, right? And there are some objects that has most planets has an orbit that's very close, even though it is an elliptical path, it's very close to that of a circular path. Okay, and what we're going to do, we are going to concentrate on the satellites that have circular paths. Okay, which is the simplest one to treat mathematically. The simplest one to treat. We will concentrate on the simple type of motion. That is the circular one. That's the circular one. Circular one, which is much easier to treat mathematically. Okay, like that. Let's see if I have. Go. Okay, right here. That's the illustration that you have. Here go. Here's a elliptical orbit. Okay, you can see it's a flattened curve. It's a flattened circle. The sun it is one of the foci of the ellipse. Okay, and here's an illustration of my satellite undergoing circular motion, uniform circular motion, by the way. Here's another illustration of the same type of orbit. And the only force acting in our satellite is the force of gravity. And the way we treat this problem is going to be illustrated by the example that I am going to solve here in class. Consider a satellite orbiting the Earth under uniform circular motion. The mass of the Earth is big M, and the mass of the satellite, consider a satellite, and the mass of the satellite is a distance r from the center of the Earth. Find the satellite orbital speed. The only force applied to the satellite is the gravitational force from the Earth. Okay, that's the only force. And then we gotta do what we have been doing to all the problems that involve forces. We gotta come up with a free body diagram. Okay, gotta come up with our free body diagram. And I'm gonna emphasize that we are going to go. Here is in the free body diagram, we must isolate our satellite from everything that exists, right? It is as though the satellite is the only thing in the universe. And then you look for all the forces being applied to the satellite. Here is the free body diagram. Okay. And the net force applied to the satellite, just using Newton's second law of motion and Newton's law of universal gravitation, the net force applied to the satellite is mass times acceleration. Okay? But the only force acting in the satellite is the force of gravity. Force of gravity, F sub g. Okay, which is, by the way, equal to the constant, universal gravitational constant, mass of the satellite, mass of the Earth, and the distance that the satellite is from the center of the Earth. But keep in mind that since it is a uniform circular motion, the acceleration that we have must be the centripetal acceleration, which is written in terms of the velocity square, the orbital velocity square, divided by the radius. Okay, and that's the velocity, the speed, the orbital speed that we want to find out. I'm gonna emphasize here, bold face it, and I'm gonna here write my equation, okay, in the way it's supposed to be written. This term here is equal to this term here, right? The only force applied to the satellite is the force of gravity, nothing else. There is no friction out there in space. Any frictional forces are very small, can be negligible compared to the gravitational force. Eventually, the satellite orbit decays because there is a little bit of atmospheric drag there at the altitude of the satellite. but it takes a long time for it to fall off from its orbit. But for the sake of this course, we can neglect those atmospheric drag. And look, I didn't tell you what the mass of the satellite is, right? But we do not need to know the mass of the satellite. To find out the velocity, we don't need to know the mass of the satellite because the mass of the satellite cancels on both sides. So let's go to the next step of the equation. Here you go, mass cancel out with mass. Okay, and then we can cancel the radius as well. Here you go, the radius, cancel out the radius. V squared. And now we finally have an equation for the velocity of the satellite. The G we know is a number that we know. The mass here is the mass of the Earth that is documented. R is also known because it was given by the problem, right? The distance R. Soon afterwards, okay, we can now solve for the velocity. And the velocity is going to be the orbital velocity of our satellite is going to be this square root here. We don't need that. Here you go. And now that's the equation. Now we're going to go for another example in which we are going to apply a numeric values for some specific satellites. Okay, so here you go. So you can have an idea of the orbital velocity of satellites that are in orbit. Let the altitude of the satellite from the surface of the sea, mean sea level, right? From the mean surface of the sea, mean sea level, be 400 kilometers. 400 kilometers is which is the average height of the space station. ISS, okay? Find the numerical value of the orbital speed of the satellite at this height. Okay. It has been established that anybody who flies above 100 kilometers of altitude or above, right? At 100 kilometers altitude or above becomes an astronaut. So if you somehow find a way to fly above 100 kilometers of altitude or above, you can claim that you became an astronaut. You don't even have to orbit the Earth. All you have to do is to fly above this height and come back to the Earth's surface. Okay. It's a major engineering achievement to fly that much high. It's not easy. It's extremely difficult. It's very easy for us to drive 100 kilometers on the surface of the Earth from one city to another, right? But it's extremely difficult to fly above 100 kilometers. You need to have very expensive engines installed in your airplane or even in your rocket. So don't underestimate this number here that you see. We are talking about a height of 400 kilometers, not the horizontal distance. Airliners nowadays, they fly at 30,000 feet. Okay, frequently they fly frequently at 30,000 feet. 30,000 feet is just 10 kilometers. Is 1/10 of what you need to become an astronaut. But let's take a look at this numeric solution. Here you go. We gotta use this equation, right? And I'm gonna go back to my spreadsheet. Here you go. Project. Let's see, which one do I want to use? Not this one. Must be this one. Yeah, that's the one. See, I have my G here. And I want now to calculate the orbital velocity, right? V in meters per second. Okay, it's going to be I square root times G times the mass of the Earth divided by the height of the distance of the satellite from the center of the Earth. And the distance of the satellite from the center of the Earth is going to be the radius of the Earth plus 400 kilometers, which is 400,000 meters. Gotta put another one. Let's see if I have it. Yeah, I have it. I'm gonna do even better than that. I'm gonna put the height here of the satellite in meters, right? And then 400,000 meters. And I will, here you go. And look what the number that we get. I'm going to change the format of this number instead of, okay, that's how fast a satellite must move before it gets into orbit. Is a huge number, is 7,671 meters per second. Okay, I don't want the decimal places there. Is 7.5 kilometers per second. That's how it's so difficult to fly, to not just to fly, but also to orbit an object. The object must be flying very fast. This speed that you see right in here is like 20, 25 times the speed of the sound, okay? I'm gonna put here in max speed so you can have an idea of, here you go, 7,772 divided by 330 meters per second, which is the speed of the sound in air, is almost 23 times the speed of the sound. The difficulty of flying to space has to do with the speed. It has to do with the speed. You have to be flying very fast to fly into space or to be inserted into orbit. And there are very few vehicles that are capable of reaching this type of speed. In order for you to fly into space just 100 kilometers high, which is considered a suborbital flight, you just enter in space and you return. You don't orbit the Earth, right? You need to fly at least 4 times the speed of the sound, 4 or 5 times the speed of the sound. Not every vehicle can fly that fast. And then there are other problems too. It's not just the speed. There are other problems too because the engine must be able to react without oxygen, right? As you fly higher and higher, you run out of oxygen. Engines nowadays, they require oxygen for combustion. Okay, that's why we have rocket engines. Or in the case of rocket engines, they carry their own oxygen in their tank, because as the rockets fly higher and higher, the air becomes more and more rarefied. But that's the type of speed that you are talking about. 7,672, right? Here you go. Going back to my notes. I'm gonna put the numbers here. 6.67 times 10 to the minus 11. Okay, and you have all that unit in Newton meter square over kilogram square. That's the unit that we are talking about. The mass of the Earth, is a ridiculously high number, 5.97, which can be approximated to 6. Okay, 6 times 10 to the 24. And then the distance of the satellite from the center of the Earth is the radius of the Earth plus the height of the satellite. Okay? And we have one more I'm gonna put the multiplication here, multiplication sign here. The radius of the Earth is 6.37 times 10 to the 6 times 10 to the 6. And the height is not 10 to the 6. 400,000 kilometers, right? It's going to be 4 times 1, 2, 3, 4, 5. 400 kilometers. Okay. The units here are kilograms. The unit here is meter. Right? Meter cancels out this meter. Kilogram cancels out this kilogram. And then you have Newton meter per kilogram. Am I missing something here? Let me see if I'm missing something here. Oh, we are talking about velocity, right? Okay, we have the meter cancel out with the meter elsewhere. This kilogram cancel out with the other kilogram, right? And then we have to do the dimensional analysis. Let's see, let's do as much as we can here. I'm gonna put 10 to the 5th outside the parentheses. If I put 10 to the 5th outside the parentheses, we end up just with 10 here, and it's gonna become 63.7, right? 24 cancel out with 5, becomes 19. Here is gonna be 67. What I want, let's see, what I want to do, let's see, 19, let's put 19 here. So this 10 to the 5th disappear. Here becomes 67.7. I just want to make sure that the units are correct. And now I'm going to multiply this one by this other one. It becomes 8 to the 8, right? So we don't have that anymore. I'm gonna move those units to the extreme right of this square. Look at this number. This number here is almost 10 times less than this one here, right? So we can cancel them out. This one, it becomes a tenth of that. It's less than a tenth. It's gonna be less than 1/10 because it's more than 10 times. Okay, but let's take a look at the units that we have right here. Newtons is kilogram meter per second square, right? I just want to make sure that this thing is in meters per second. Kilogram cancels out with kilogram. This meter combined with this other meter, right? Becomes meters per second square. And what is inside the square root is meter square per second is meter square per second square. And it seems that from the viewpoint of dimensions, we did everything right. Okay. If you do the math, you get that as being 7,672 meters per second. Here you go. Which is 7.67 kilometers per second. And like I said, it's very fast. Do not underestimate this speed. Kilometers per second. Imagine flying at this speed. You can cross the United States in 15 minutes only. Okay? Flying at this speed, something like that, right? 15 minutes, divide, 15 minutes. Let's see how far can we travel in 15 minutes at this speed. At this speed, we can go around the Earth in 90 minutes at this speed. Only 90 minutes, okay? The continental United States has 3 time zones. Okay, no, has 4 time zones, the continental United States. 1, 2, 3, 4. The whole Earth has 24 time zones. Okay, 24 time zones. 24 divided by 4. I'm doing the back of envelope calculation. Is 6 times more. So if you orbit the Earth in 90 minutes, 1 hour and a half, and that's what happened to the space station, you'll be able to cross the United States in 90 divided by 6. 15 minutes, just like I said. Okay, at this speed, you can cross the continental United States in 15 minutes. And the United States is a huge country, right? One of the largest countries in the world. There's a continental dimensions. In 15 minutes, have you imagined? In order to fly from Los Angeles to Florida, which is crossing the continental United States, it takes 5 hours with a regular airplane, right? With a regular airline that flies subsonic. But if you are able to build an airplane capable of flying that much fast, and then we call that hypersonic speeds, you'd be able to do your trip from Los Angeles to Florida in 15 minutes. Wouldn't that be nice? Okay. And fly around the Earth in 1 hour and a half. Okay, and that's the orbit. Let's see, let an object of let's see here. We have another example here. Okay, here's an example of how to find the mass of a planet. Okay, and astronomers do this type of thing, how to find the mass of the sun, for instance. We can find out the mass of the sun if you know the orbital speed of the Earth, for instance. If you know the orbital speed of the Earth, you can find out through other means, right? Not just the orbital speed of the Earth, but the orbital speed of any planet or any satellite. You can find out the mass of a larger object. All you have to do is to use that equation that we derived before. Okay, here you go. Here the mass, unknown mass, right? Suppose that you know the velocity of your satellite. You know the distance of the satellite to the center of the Earth. Find the mass of the Earth, right? Let an object in a circular orbit be, you got an object be in a circular orbit around a larger mass, given its orbital speed v and its distance from the center of the larger object, find the mass of the larger object. All you have to do is use that same formula that we used before. Okay. But now we are using the formula for a different reason, right? For a different goal, for a different problem. We want to find the mass of the central object. It's going to be v squared over r divided by big G. And that what's going to be the mass of the larger object, v square r over g. And then we can play with numerical examples. Okay, find big M. Find big M for the following values. Velocity of 750 kilometers per second, which is, wow, that's a lot. It's a lot. I wonder where I got that value. The orbital speed of the Earth is 36 kilometers per second. But this one, I suspect that this one must be orbiting a black hole. And that's the distance in meters, 10 to the 17. I suspect, let's see, let's do the math. Let's do this solution. Here you go, the numerical solution. And again, we are going to use our spreadsheet. Okay, so here you go. We want to find the mass of the object, right? We do have the V, we have must be in meters per second. We have the radius, and we want to find the mass of this object. I'm suspecting it's a black hole, but let's do the math. I myself don't remember what I got at that time. Okay, so here you go, 750,000 meters per second. The radius is 5.7 times 10 to the 17, 5.7 e to the 17. That's how Excel treats 10 to the 17, right? And we write down the equation for the mass is v squared times r, the distance r, divided by big G, which is already documented right here, big G. I'm getting 4.8 times 10 to the 39 kilograms. 4.8 times 10 to the 39 kilograms. Okay, mass. Uh, 4.8 times 10 to the 39 kilograms. Now let's compare this mass with the mass of the sun. Now let's compare that with the mass of the Earth first. You already know what the mass of the Earth is. And then we move to the mass of the sun, right? This guy, I'm gonna divide one by the other, is several orders of magnitude more. We're talking about 15 orders, almost 15 orders of magnitude, the mass of the Earth. This object is 8.05 times 10 to the 14 orders, almost 15 orders of magnitude, the mass of the Earth. The mass of the Earth. Okay? You can get the mass of the Earth from any book. out there. And what about the mass of the sun? Let's take a look at the mass of the sun. Let's see how it compares with the mass of the sun. Mass of the sun is, it's 5 orders of magnitude, no, 9 orders of magnitude more than the mass of the sun. So that looks like a black hole to me, a supermassive black hole. Let's see. This object is, let me go back to my, here is the, I'm gonna emphasize that what we have here is the mass of the Earth. Okay. And that's what I did here. I divide this mass by the mass of the Earth. And let's put the mass of the sun here. Mass of the sun in kilograms. Subscript 1.89 1.989 e to the third. Okay? And then we divide this mass here by this mass. Okay. I'm gonna put it here, mass of the Earth. Mass, we go. And this one, I'm going to switch sun. Right, there is no unit here when you take the division between them. So let me take this thing out. Okay, here you go. Emma divided by this Emma. We are talking about, no. What happened here? I divide by the wrong thing. Let me do that. Let me do that right. Here you go. Mass is this one here. Yeah. 2.42 times 10 to the 9. Okay. Let's take a look at the Wikipedia. Masses of supermassive black holes, okay? Of supermassive black holes. Let's see. Supermassive black holes masses range from approximately 10 to the 6 to 10 to the 11. Our black hole, right? Our example has a mass of 10 to the 9. So it is a supermassive black hole. In the case of the Milky Way central black hole, the mass of the black hole is 4 million times the mass of the sun. Okay, so it's still the supermassive black hole at the center of the galaxy is still smaller than the mass of our black hole in our example. Okay, that's the type of games we can play. This object is 2.42 times 10 to the 9. Yeah, 2.42 times 10 to the mass of the sun. Consequently, this must be a super massive black hole. we are reaching our point where we are going to have our break, right? Okay, let's do another example before we go in our break. Hopefully we'll be able to do that in less than 4 minutes. Example, there is another important application of satellites. You must have heard about geosynchronous satellite. Those are very important. And a geosynchronous satellite is a satellite that orbits the Earth in a period of 24 hours. It's in synchrony. It's called geosynchronous satellite because it's in synchrony with the period of rotation of the Earth. Okay, this satellite is called this orbit satellite. No, let's put the satellite and its orbit, right? Not the satellite and its orbit is called geosynchronous because it is in synchrony, because it's synchronized. It is synchronized with the Earth's rotation. Okay, this is the type of satellite. This is the type of satellite that appears at the same spot in the sky. It never moves from that spot in the sky. Okay, same. If let's say if the satellite is in a geosynchronous orbit, it will be always at the same height and same azimuth in the sky. Okay, so let's say 45 degrees from the horizon, right? And let's say 35 degrees from the northern direction. The satellite would always be at that spot in the sky. This is the type appears at the same spot in the sky. This type of satellite is very useful. This type of satellite is very useful for telecommunications. Okay, so if you're at your home and you're receiving a signal, a TV signal from this satellite, and I used to have signals from those satellites, right? You can get an antenna, it's a parabolic antenna, pointed towards that spot in the sky. And the antenna doesn't have to follow the object since it's always at the same spot in the sky. So the antenna is very simple. No need to have motors to move the direction of the antenna from one spot to another in the sky. This type is very useful for telecommunications. For instance, if you have satellite TV service, you will need a parabolic antenna pointed to the position on the sky where this satellite is located. Okay, so there are a bunch of geosynchronous satellites in orbit. Let's take a look. They're so, it was Arthur Charles Clarke, it was the science fiction writer Arthur Charles Clarke, the guy that wrote 2001, okay? Science fiction writer Arthur Charles Clarke. Arthur C. Clarke. The guy that wrote 2001 and 2007, which ended up being a movie, two different movies. The movie 2001, which is a classic in the movie, right? And it's not just a classic of science fiction, but it's a classic, a screen classic. And 2010, that was just the continuation of 2001. I do not know if you watched those two movies. 2001, I believe, was made in 1969 by what's his name? What's the name of the director? A famous director, the same guy that did the Clockwork Orange. You know, he's already died. What's his name? I will remember his name. Okay, and 2010 was launched in 1984, 1985. You know, launched. I had a friend that collaborated, a Brazilian friend that collaborated with Arthur Charles Clarke in this movie here. But he was doing just for the fun of it. He was not being paid. He was just writing letters to Arthur Charles Clarke, and Arthur Charles Clarke was replying to him. Stanley Kubrick. Here you go. I remember. Stanley Kubrick. That's his name. Directed by Stanley Kubrick. The movie was launched in 1984, right? And it was Arthur Charles Clarke who described the usefulness of a geosynchronous satellite. Many people claim that he should have patented this idea. I do not know if he could patent it. I don't think he could it. Let's take a look. Geosynchronous satellite. I think this idea of geosynchronous satellite was already around before Arthur Clarke. Let's take a look here. Geosynchronous characteristics and function. Let's see here. I want to see the history behind that this geosynchronous satellite. Definition, application. Let's see history. I want to see the concept was first proposed by not Arthur Clarke, but Herman Potonik, right? In 1928, and it was popularized by Arthur Charles Clarke. So Arthur Charles Clarke did not invent this type of satellite. So he could not patent because it was first proposed by this guy in 1928. It was an old idea already. Maybe he could have patented other things, in this. And it was a paper he wrote. It was not a short story, a science fiction story. Wireless World, technical magazine published by Data Team Business. It was during the war. Arthur Charles Clarke worked during the war as a radio frequency engineer. He was working in the projects of when the British was developing the radar to detect incoming missiles and planes during the war. Okay, and he came up with this idea, and then after the war, he became a very famous science fiction writer. Okay, envision a trio of large crewed space stations arranged in a triangle around the planet. Modern satellites are numerous, is uncrewed, and often no larger than an automobile. Father of the geosynchronous, widely known as father, Harold Rosen. Okay, Harold Rosen is the father of geosynchronous satellite, an engineer at Hughes Aircraft Company. I believe it's in Los Angeles, okay, this company here. Canoga Park, I presume. Invented the first operational geosynchronous satellite, it was Synchron 2. It was launched in a Delta Rocket B booster from Cape Canaveral, July 26, 1963. Okay. First geosynchronous communication satellite, or Synchron 3. But let's see, what is the orbit, the distance of the orbit of a geosynchronous satellite from the center of the Earth, okay? You already know. Here you go, solution. Let's put here. Before we calculate that, solution. You already know that a satellite at 400 kilometers high has around the center of the Earth, okay? The center of the Earth, not around the Earth, but around the center of the Earth in 90 minutes, 1 hour and a half. If you climb higher and higher, it is possible to prove mathematically. If you climb higher and higher, the period of your orbit increases, okay? Of your orbit increases. It's possible to prove that. And using the same equations that we have derived before, okay? So here you go. Let's take a look at this equation, for instance, this equation here, okay? This equation for now doesn't have the orbital period yet. Refer to the equation we derived. Okay, here you go. The orbital speed of a given satellite decreases as it moves further and further away from the center of the Earth. Do you see that? Goes to the square root. Okay, we can even plot D against R. It's possible to do that. G doesn't change, it's a universal constant. M doesn't change because the satellite is orbiting the Earth and the mass of the Earth doesn't change. Okay, but what about the period? How can you come up with the period, right? From the above equation, we can see that the orbital period of a satellite decreases with its distance from the center of the Earth. Okay. What about its period? What about its period? Okay. We are considering, remember, since we are considering uniform circular motion, the speed of the satellite can be written in terms of its period, right? Of the period, not its period, but in terms of the period that it takes to orbit the Earth. Okay? So how do you do that? Here you go. This equation can also be written, this velocity can also be written down in terms of the circumference of the orbital, the orbital circumference, which is 2 pi r, divided by the period. That's how you do it. Okay? And now we have a relation between the period and the distance from the Earth. Okay? Because it's a uniform circular motion. This speed that you see here is nothing but the circumference, the orbital circumference, divided by its period. And what do we want? We want to find out the distance of the satellite from the center of the Earth for a satellite that has a period of 24 hours. Okay? So here you go. We can write that as, take the inverse. When we take the inverse T 2 pi r, T over 2 pi r over r gm, right? We're taking the inverse of both sides. That's what we're doing. Like that. Here you go. And now we want to know R, right? R for T equal to 24 hours. That's what we want to know. So I'm going to emphasize here, find R for T equal to 24 hours. And then you can check with the internet what, if your R is correct. So let's see how we're going to do. I'm going to square both sides of this equation. square square square. I want to write down R equal to something, right? Oops, no. Now for pi square R square. Here you go. That's how we do it, right? And now solve for R. In order to solve for R, I have to pass my R to the other side, and it's going to become R cubed, right? R squared times R. And I'm going to pass GM to the other side. You go. R cubed. And then what you're going to have, we're going to have the cubic root of this term that you see right here. Cubic root. Oh, heck. That's okay. Okay. And now we have to substitute 24 hours here. 24 hours times 3,600 seconds, right? 24 times 3,600, because everything must be in the regular units of the SI system. And let me get my spreadsheet again. Okay. Period. No, I want R, right? R. And the period. We want an equation here. Period should be 24 hours times 3,600 seconds, right? And my equation here should be the cubic root. Cubic root. Let's see here, and let's go back to the numbers. Big G, big M, right? Big G, big M. Big G times big M times period T. That's going to be V2. V2 divide, let me see if I'm forgetting something else here. Oh, it's T squared, by the way. T squared. So V2 squared divided by 4 pi squared. Divided by 4 times pi square, close parentheses. Right? Let's see, everything looks good. 4 pi squared is downstairs. That's why I have this parenthesis here. Okay. This guy should be raised to the 1/3 of a power. That's why I have this other parenthesis here. And now let's take a look. We're getting, let's see what this number is. It's 42,200, 42,200,000 meters. Okay, here you go. And I'm going to divide that by 1,000 to get that in kilometers, so we can understand this number better. 1, 2, 3. And I'm gonna put that in the regular format. Number, no decimal places. Here you go. 42,000 kilometers. And then we can double check with the result in the Wikipedia, right? 42,000. Let's see here. Where is the height? Maybe we should go back here. Geosynchronous satellite. Geosynchronous are at an orbit of approximately 35,000 kilometers. Okay, 35,000 kilometers is in reality the distance from the surface of the Earth. Okay, if you sum that with 6,000 kilometers, you get the 6,700 kilometers. You get the result that I got. Okay, he didn't say that, but 35,000 kilometers is the height of the satellite, not the distance from the center of the Earth. See, altitude, right in here, altitude. It's not the distance from the center of the Earth, altitude above the equator. So the number that we got is correct. Okay. We can also calculate the speed. What's the speed of the satellite? Let's see. Let's make sure that the speed that we get matches what we have here, right? Let's write that down here. 37. 3 more minutes to go. Okay, be patient with me, and then I want to. Here you go. This one. According to Wikipedia, right? R kilometer, is 35,786. 35,786 plus the radius of the Earth. The radius of the Earth, it's in meter, divided by 1,000, and look what we get. We got the same thing, right? We got the same thing that I got here. Okay, let's put that in numeric format. Maybe there's a small difference, less than 1% difference. Use, you can see, right? Just 100 kilometers difference, less than 100 kilometers difference. 100 kilometers difference here is less than 1%. Is 1/4, is less than 1/4 of a percent. So that's Wikipedia. That's the value in Wikipedia. That's the value we calculated. Okay. And then we can calculate too, using the above number. I'm going to do that. Let's see, homework, right? Homework. Using, let me write that down here. 42,235 kilometers from the center of the Earth. Don't forget, this is the distance. Don't forget that this is the distance from the center of the Earth. Okay? Homework. Using the above number, the above distance, find the orbital speed of your geosynchronous satellite and compare with the number in the internet. Okay? In the internet, this number is 7,000 miles per hour, 11,300 kilometers per hour, okay? So we can stop now and have our break so you don't get burned out. Okay, break between 11:05 and 11:20 a.m. Any questions? Let's see, am I missing anything? Okay, so I'll talk to you soon. See you soon. Thank you. Bye-bye. I am back here. So let me illustrate how exactly the correct name for this orbit that we are talking about is not geosynchronous, but is geostationary. Okay. There are several types of geosynchronous orbit out there, and geostationary orbit is just one type of geosynchronous orbit. Okay, let's clarify that. Let's make it clear. So, and notes right in here. Okay, just to clarify, just to clarify what we discussed. Okay, you know, there are several types of geosynchronous orbit. Okay, and the one that we described and the one we described is just one type of geosynchronous orbit. Okay, geosynchronous orbit. Let me called geostationary orbit. Okay, this one that we discussed is a geostationary orbit. Okay, so what exactly the difference, right? So a geostationary orbit, which is one type of geosynchronous orbit, is this orbit that you see right in here. Here you go. And let me elaborate what you see here. What you see right in here is the North Pole of the Earth, okay? What you see right in here. So you're looking from the North Pole of the Earth. Let's see here. Yeah. Let me get this thing bigger. And what else? That's the North Pole of the Earth, right here. And this plane that you see here coincide with the plane, with the equatorial plane of the Earth. Okay? Make sense? Okay, so the plane, the orbital plane, this orbital, when the orbital plane of the orbit coincides with the plane of the equator of Earth's equator, of the Earth's equator, comma, then this geosynchronous orbit is said to be a geostationary orbit. Okay? So, very important difference here, okay? A geostationary orbit is just one type of geosynchronous orbit. And I'm going to illustrate exactly what that means. Okay, so here you go. Let me eliminate here this thing. Okay, and let's see if I can. I'm going to rotate. Here you go. Here is a point. I'm going to put a point on the Earth's surface, which coincides with the equator, right? Here you go. There's a point on the equator of the Earth. I'm gonna put, let's see, which color? Red color, right? Someone sitting down on the Earth equator, and he's looking a point on the Earth equator. Okay, so that's a given instant of time. Okay, so here you go. And now a little bit later, oh, I cannot ungroup this thing. Oh gosh, what a shame. Let's see if I can get it. This one, no. Oh, that's gonna be, what a nasty thing. Okay, so if once the Earth, if the Earth rotates just a little bit, I'm gonna, let's say, rotates 15 degrees, right? Here you go. Here the Earth rotating, right? Oh, wait a minute. No, 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 no. That's not what I want. I want, hey, gosh. I want everything here. Now, group, okay? What is a geostationary orbit, right? So here you go. Now I can rotate. Now, do you see everything rotate? When the Earth rotates, the satellite accompany the Earth's rotation. So whoever sits at some point along the equator of the Earth is going to see this satellite. The satellite is this one right in here, right? And in the same spot of the sky. That's what a geostationary orbit is all about, which is a type of geosynchronous orbit. Okay? Got the idea? The angular velocity of the satellite is the same angular velocity of the Earth. That's what this orbit is all about. Let's see, I'm going to erase this one because we do not need it anymore, right? I cannot, oh my goodness. Yeah, what a shame. I want to erase this force here, but for some reason I cannot do that. I'll leave this way, okay? So do you see the relative position of the satellite is the same? The stars in the background, the sun, the moon, the stars in the background, they're still rise in the east and settle in the west, but not the satellite. The satellite stays at the very spot in the sky. Okay. Now, what about other geosynchronous orbit? Another geosynchronous orbit is an orbit in which the plane, the orbital plane, does not coincide with the equator. It's a little bit inclined, okay? It's a little bit inclined. And we have an illustration, not this one, the other one. Here you go. This one right in here. We have this illustration right in here. See that? That's a geostationary orbit. Oh, gosh, what is this guy? The blue one is a geostationary orbit. And here is a more generic, the red one is a more generic geosynchronous orbit in which the satellite is at the same height, but it doesn't stay stationary in the sky. It moves a little bit. It moves just a little bit, okay? So the most valuable orbits, of course, are those ones that the orbital plane coincides with the equator of the Earth, the geostationary one. But as we put more and more satellites on this orbit, eventually it gets too crowded and you cannot launch more satellites in there. So people decide to use other types of orbit that's still, is still considered a geosynchronous orbit, but it's not as valuable as the geostationary one, okay? That's a very important difference here to keep in mind. And we can move forward now. We are done with satellites in circular orbit. Like I said, we are not going to cover the other types of orbit because it's too much. It's too much to mathematically. It is very complicated. Okay. Okay, and the next one is apparent weightlessness and artificial gravity. We already covered apparent weightless. Okay, and by the same token that you feel weightless inside a free-falling elevator, you will also feel weightless while orbiting the Earth. Okay? And everybody has seen the astronaut floating inside the space station, right? And there is a real, and the same effect that they feel there in orbit is the same one that we feel here on Earth whenever we are inside the free-falling elevator. Okay? It's possible to replicate this free-falling sensation with, for instance, an airplane. It's possible to do that, okay? It is possible. In addition, right? In addition to board an elevator that is free falling, comma, we can also fly an airplane. We can also fly an airplane and reproduce this effect for several seconds. In several seconds, I mean several seconds. Like, 20 to 30 seconds. It's possible to do that. NASA used to have an airplane that was called the KC-135, right? NASA used to own an airplane, no longer has this airplane, called the KC-135 and nicknamed the Vomit Comet, okay? That was capable of simulating this effect. Okay? I had the fortune to fly this airplane before, back in 1993. Back in 1993 and 1994, I had the great fortune of flying this airplane. And in the process, I became the first Brazilian to do that. The first Brazilian citizen to do that. Okay. And how does NASA fly this airplane? Okay. NASA flies this airplane in a parabolic maneuver, simulating the path of a projectile, the same path that we studied before. Okay? During this period, it's possible to experience 20 to 30 seconds of zero G. Okay. But this type of maneuver is not just restricted to NASA's Vomit Comet. Okay. But this type of maneuver is not restricted only to NASA's KC-135. Okay. This same maneuver can be reproduced using smaller aerobatic airplanes, aerobatic airplane. Using a smaller aerobatic airplane. And I did that before too. I am a pilot, and I used to rent an airplane, an aerobatic airplane, and perform this type of parabolic maneuvers. However, because the airplane is smaller and flies slower than NASA's KC-135, I was able to simulate at most 15 seconds of 0G, okay? 0G. And has everything to do with that equations that we developed before using Newton's second law, right? Now, how does it apply in orbit, right? Now, how does, okay, we covered that before in the section of apparent weight, right? Apparent weight. Now, the question is, how do you solve this type of problem for the case of an astronaut that is in orbit, right? Mathematically, how do you solve, right? How do you solve? The question is, how do you solve mathematically this type of problem for the case of an astronaut in orbit? In other words, how do you prove mathematically using Newton's law that an astronaut in orbit experience weightlessness? Okay, and we are going to do that. And I'm going to use the same example of our elevator, but now our elevator is in orbit. Consider an elevator orbiting a distance r from this, orbiting the Earth, a distance r from its center, right? From the center of the Earth. This elevator is equipped with a scale that measures the normal force applied to a test subject that's inside the elevator. Find the apparent weight of our test subject, okay? It's a similar problem, but now it's a problem that involves circular orbit. I can even, let's see if I can even draw it here for you. Let's see if I already have it. No, I don't have it. I have to do that from scratch. Okay, so I want to get rid of this. That, now I know what's happening here. Group, send to back. Okay, I see. Okay, no. Okay, so here you go. I don't need that anymore. I don't need that anymore, right? But I need that. Let me copy this guy here. Let's see if this one is the one I want. Yeah, that's the one I want. Here you go. Radius R, North Pole, and here you go. I'm gonna draw my elevator right in here. My elevator in low Earth orbit. Black, okay. And I'm gonna put my scale here inside my elevator. Okay, here you go. That's the scale. And my test subject on the top of the scale. Gotta be shorter, otherwise you don't fit in the elevator. Okay, here you go. I'm gonna put the indicator of the scale as well. It's not a digital scale. It is an analog scale. So you can understand. And let's zoom in, zoom in. It's just terrible. Zoom. I'm gonna zoom 200 times, 200%. Yeah, here you go. Here you go. Here's my scale, right? And here's the indicator of my scale. Here's the indicator of my scale. And the elevator is much smaller than that, okay, folks? I'm just exaggerating on the size of the elevator. And then what you have to do, you have to identify the forces that are acting on this test subject. Okay? You gotta come up with the free body diagram of this test subject of ours. Free body diagram, I'm gonna draw it for you. No fill. Line is gonna be a black one. And I'm gonna dash this guy so it's understood that this is not a solid object, but just a way of emphasizing the fact that we are looking only at the forces applied to our test subject. Okay? In this case, the forces are going to be, there will be a force that's always will be there, right? And this force is the weight. The weight is nothing but the force of gravity. Here you go. The force of gravity that's being applied to the test subject. I'm gonna write that down here. Illustrate here, W. Huh, strange. I see, I know. Yeah. Write that down. Uh-oh. W. Bold face. Get this thing a little bit larger, right? That's the weight. But then we are supposed to have another force here too applied to our astronaut, right? Which is this force is going to be the normal. Let's see here. Normal force. I'm gonna put them in the same color. Let's see, red, arrow red as well. So you have this color code. Here, I'm gonna put blue. I like this light blue here. Looks very pretty. Here you go. And W. Okay. Here's my free body diagram. And I can write down my equations using Newton's second law, just like we did for the elevator, for the case of the elevator. Okay, so here you go. Net force is equal. Well, let's start with net force is equal to mass times acceleration, right? Newton's second law of motion, like that. But my net force is also weight plus the normal, right? Weight, and the object is undergoing uniform circular motion. And because the object is undergoing uniform circular motion, the acceleration that we have is going to be the centripetal acceleration. Okay? And both the weight and the normal are going to be only, both the weight and the normal are in the radial direction. Both W and N are in the radial directions. Okay? And I'm going to, which is also along the centripetal, which is also along the centripetal direction. Now, my vectorial equation can become a scalar equation. Or, here you go. Instead of W vector, we're going to write now W scalar. Instead of N vector, we're going to write now N scalar. And those numbers can be either positive or negative. And that's going to be equal to mass times centripetal acceleration. Okay? We do know that at least the weight is in the same direction as the centripetal acceleration. We are going to find out what's going to be the normal, right? Let's not forget that the centripetal acceleration is equal to b squared over r, right? We also know that this, and by the way, let's be put here. Here is going to be centripetal force, okay? What you have here is centripetal force. And the centripetal force, we also know that's going to be given by the mass of the object, the mass of the astronaut, right? That's inside the elevator. Big G, the mass of the Earth, and the distance of the elevator to the square, R square. But let's not, here you go. Now we have this equation here. Now we have this equation here. However, let's not forget that the weight is, by definition, the gravitational force applied to the test subject. Or, the weight is going to be exactly equal to this right-hand side. Okay? Because the weight is exactly equal to the right-hand side, what does it imply? It implies that the normal must be equal to what? Must be equal to 0. Okay? That's how we prove that we feel weightless while we are orbiting the Earth. That's the way to prove it. Oh, okay. Don't forget, the weight by definition is the gravitational force. So someone that is orbiting the Earth, okay, will feel weightless. And by the way, we can come up with another type of problem that I like to discuss with my students as well. Okay. But now it is the problem of the space elevator. Problem of the space elevator. The space elevator is, let's see, instead of problem of the space elevator, problem of a very high tower, that is 100, even more than that. Let's put 400 kilometers high. Have you thought about that? Inside this tower, there's a space elevator. Inside this tower, there is a space elevator that can take human beings to orbit. Not exactly to orbit, but to the height of an orbit, right? There is an elevator. There's an elevator that can take our test subjects to a height of 400 kilometers. Okay, and I'm going to illustrate that here. So now you're going to see the difference between something orbiting the Earth and something attached to the Earth, which is not necessarily orbiting the Earth. There's an important difference between these two situations, okay? So here you go. Let me do that here. I'm gonna erase this thing. Oh, okay. And now send to back. Let's see. Send to back. Let's see if I can get that. Yeah, okay, good. R. Yeah, now I can. Good. And now what we're gonna have? We're gonna have a very tall tower. Can you imagine that? Attached to the surface of the Earth. And because it's attached to the surface of the Earth, it's not orbiting, the tip of the tower is not orbiting the Earth in its proper sense. Okay? In its proper sense. So here you go. And now you're going to start understanding the important difference between an object orbiting the Earth and an object, a major structure, major engineering feat. Have you thought about that? Building a tower that's 400 kilometers high. Nobody has ever built that. Taller than the Mount Everest. Taller than the Mount Everest. And then there was a movie, right? Brad Pitt's movie. I forgot the title of the movie. Who watched that movie? Anybody watch that movie? In which they dramatized this tower. What was the title of the movie? Anybody remember that? Just a Brad Pitt movie. How long? It might be like 5 years ago. And they described this tower. Anybody watch that movie? Whoever is a fan of Brad Pitt? Brad Pitt movies? Science fiction movies, right? Brad Pitt science fiction movie. Science fiction movies. Let's see. Oh, I hate that. My VPN is interfering with my search. Okay, now that's why I keep on getting this thing. Oh, system of unusual traffic. What the heck's going on here? Let's try it. Let's try it again. Brad Pitt science fiction movies. Ad Astra. That's the movie. Anybody has watched this movie, Ad Astra? Let's take a look at the trailer. The trailer should show.
What are you thinking about?
I do what I do because of my dad.
Okay, here's the tower.
Usually,
Oh, well, I'm gonna go back here. Here's the tower. The tower that they built in the movie, right? With an elevator. It's attached to the surface of the Earth.
usually
100 kilometers high.
he gave his life for the pursuit of knowledge.
Here you go. And now he's climbing. Imagine you 100 kilometers high on Earth, climbing this stair. That's 100 kilometers high and staring at the Earth down there. Right? There you go. Oh, see? They dramatized the whole thing. They made it very realistic. I like those movies when they make it extremely realistic. Here you go. And then something happens. If you watch the movie, he falls from that altitude. The same guy, you know, something happened to that guy that jumped from the balloon, right? And here you go. And now he's falling from that height. He cannot open his parachute yet because there's no air at that altitude for the parachute to dump his fall, right? Let's see if you have any more.
There's fires everywhere and plane crashes. They're calling it the surge.
Yeah, so that's what I want to show in this movie, the tower. And that's what I'm depicting here. You know, here's the tower. Brad Pitt here at the top of the tower. And Brad Pitt is now at the top of a scale as well. There is a scale. Okay, here you go. The scale at the top of this orbital tower. It's not an orbital tower because it's not orbiting the Earth. It's not orbiting the Earth because it is attached to the Earth, right? We already know that orbiting satellites go much faster than the rotation of the Earth. And now the problem changes. The problem changes somewhat. The problem changes somewhat because the orbital velocity of the tangential velocity of the tower is not going to be equal to the orbital velocity. It's going to be less than the orbital velocity. Okay, and now I can zoom in into my test subject, right? Here you go. I'm gonna make it larger. Let's see here. This guy goes away. Here you go. Brad Pitt again. Here you go. The scale that Brad Pitt is using, make it larger. Here you go. Right? And we're going to have the same things here. We're going to have the weight of Brad Pitt. That's my free body diagram. And then we're going to have the normal. course, that the scale applies to Brad Pitt. Here you go. It is moving in a circular, uniform circular motion. Yes, it is moving. But the velocity is not going to be the orbital velocity. It's going to be less than the orbital velocity. Here you go. I'm going to put the velocity here. That's an important difference between the other problem that we have. Here you go. Velocity vector. Velocity vector. Here you go. I'm going to put it in the black color. Okay. And what do you want to do here? What time is that? Are we running out of time yet? 12:01. We still have 50 more minutes to go, right? Problem of very high tower that's 400 inside the tower. There's an elevator that takes our subject, our test up to a height of 400 kilometers. Calculate, right? Calculate the apparent weight of our test subject at the top of this tower. Then repeat this calculation for a tower that is that has a tip. Then repeat this calculation for a height equal to that of a geostationary orbit. Okay. Now we are using the right word here. There's a difference between geostationary and geosynchronous, right? Geostationary is just one type of geosynchronous orbit, the most useful of them. Here you go. Problem example. For a tower with a height equal to that of a stationary orbit. And don't forget, it's very difficult to construct, to build something like that. Okay, it would be a major feat of engineer to build a tower that 100 kilometers high. The highest, tallest buildings in the world, we can look at the internet, doesn't come any close to that. Tallest buildings in the world. Let's see here, in Dubai. The United States used to have the tallest building in the world. Right now, it's countries like Dubai and Malaysia has the. It's only 800. It's less than 1 kilometer, folks. What we have built so far, the tallest thing that have built so far, is less than 1 kilometer high. 100 times less than what would need to go into space. Just to emphasize how difficult it is to build something like that. List of tallest structures. Let's take a look. Here you go. This one here. Khalifa must be the one in there. Yeah, Mega Tower skyscraper in Dubai, United Arab Emirates. This one must be in the Malaysia. Yeah, that's in Malaysia, Kuala Lumpur. See, United States no longer has the tallest buildings in the world. A Tokyo Sky 3. Tokyo Sky 3 opened in 2012. 634 meters. Now think about that. We're trying to build something that's 100 kilometers high. This is small potatoes compared to what we want to build, right? Compared to what was described in that science fiction movie. And we have Shanghai Tower. Okay, only 632 meters high. What about this one here? This one is in North Dakota, United States. But it's not a building, right? It's a mast. It's a TV tower. Okay. We're talking about, don't forget, we're talking about tallest structures, not tallest building, right? We're talking about tallest structures, not tallest buildings. For you just to have an idea of the scale that we are talking about here. Here you go. Here's the orbit, here's the velocity, right? So what we want to know, we want to calculate the normal, apply it to our test subjects. That is going to tell you the apparent weight of our test subject. Okay? And now we are going to see clearly the difference between an object that's orbiting the Earth and orbiting the Earth, let's say at 400 kilometers high, and another object that's sitting at the top of a 400 kilometers high tower structure, right? Solution. You already know that the apparent weight of an orbiting object is 0. Weightlessness. What about the apparent weight of this object that's sitting at the top of the tower? Okay, we do exactly what we did before. Okay, net force. Let me just copy what I did there at the top. Here you go. We're going to do exactly what we did before. Here you go. Net force is mass times acceleration. Net force is going to be the weight plus the normal. It's going to be along the radial direction. Mass times acceleration in this case is going to be, the acceleration is going to be the centripetal acceleration. But now the centripetal acceleration is still written in terms of the, let's see here. It's going to be written not in terms of the orbital velocity, but in terms of the rate of rotation of the Earth. Okay? That's the important distinction. That's the important distinction between our orbiting object and our tower attached to the surface of the Earth. Here you go. Centripetal force, and the net force is going to be our centripetal force, right? Let's write that down here. And let's see, I'm going to even put it here like that. Here you go. The net force is equal to our centripetal force. It's the weight plus normal. Both the weight and the normal are directed along the radial direction. One is in the negative radial direction. The other is along the positive, maybe along the positive radial direction. And the centripetal acceleration is going to be always towards the center of the Earth, right? But now don't forget, now this velocity is no longer an orbital velocity. Okay, here you go. And because it's no longer orbital velocity, we cannot say that the centripetal force is going to be equal to the force of gravity. Okay? What's going to be equal to the force of gravity is this term here. That's the term that's going to be equal to the. So I'm going to correct that here. Here you go. And I'm going to use I'm going to use like the negative direction, okay? Because it's towards the center of the Earth. So I'm going to here write this equation in terms, here you go. I'm going to substitute that right in here. Now the sign makes a difference because the normal before was 0, right? Before it didn't make a difference. And here you go, this velocity. This velocity, in that previous problem, this term here ended up being equal to this term here. And by the way, because the weight is negative, this one must be negative as well. The centripetal acceleration must have the same direction as the weight. And I have to replace the velocity here. Here you go. Now I have to replace this velocity with 2 pi r. R is going to be the radius of the Earth divided by the period of rotation of the Earth. Do you see the difference now? Do you see the difference now? I'm going to even name that V prime so you know it's, so I can emphasize that this velocity is going to be different from the other velocity. Compare V prime with the other V, with the V of the other problem, right? The other problem. Here you go. V prime. Let me copy that. I'm going to put them side by one below the other, right? Not side by side, but one below the other. V prime. We're going to have our break very soon. V prime is 2 pi r over t. Don't forget, r is the radius of the Earth. And the other V, let's see here. The other V is this one, is related to this one here, right? Calculate that before. Let me get that. Here you go. Okay, this one here. One is the orbital velocity, the other is the tangential velocity of the Earth at the equator. But wait a minute. There is more to it. It's not the radius of the Earth, not just radius of the Earth. It's actually radius of the Earth plus the height, right? Plus the height. But the height is much small compared to the radius of the Earth. See, those two are definitely different from each other. Okay? Note, see that, you know, we're going to have our break very soon. Different. V prime. Like that. So that's the major difference. And I gotta put R plus H here. R plus H. Okay. Here you go. The top of the building has a speed greater than the bottom of the building. The top of the tower has a speed greater than the bottom of the tower. 12:14 right now. I think we are going to have our break and then we finish, right? We finish this problem when we return, right? Lots of good problems here for you to play with, right? It is 12:15 now. Break. 12:15 p.m. to 12:30 p.m. now. So let's have our break now, and I talk to you soon. Okay, let's see here. Someone is asking me a question. When will we choose the date for the test? Oh yeah, let's come back For now, the test is still set for that date that was initially, okay, originally scheduled, okay, Edith? For now. We still have time to. Okay, so unless I tell you otherwise, it's still that date that has been originally scheduled. Let's see here. I am back here. Let's finish this problem. We're spending too much time in this chapter, right? Let's see if we can finish it here. And we're trying to calculate the normal, which is the apparent weight of our test subject. Here we go. The equation that we have so far is this one here. Here you go. That's the equation we have so far here. It's this one right here. And that's what we want to find out. And let's see, by the way, we need to know the way, problem very high tau. Inside the star, there is an elevator that takes our test subject, calculate the apparent weight of our test subject at the top of this tower. Assume that the mass of our test subject, we need the mass in this case, is 80 kilograms. Okay, 80 kilograms. So we need that, otherwise we won't be able to solve this problem. That's the equation that we have. So all we want to do is to calculate this value right here. Okay, let's not forget that lowercase r. What's going to be lowercase r? It's going to be the distance of our test subject, the tip of the tower to the center of the Earth. Same thing here, right? So let's solve for the normal. This guy goes to the other side, becomes positive, right? Since this one is positive, I want to put this one here to the other side and erase this sign.
Professor, you're not sharing your screen.
Oh, thank you, thank you. Thank you for reminding me. Here you go. Screen. What about now? That's good, right? Okay.
Yes,
So
good.
okay, so what did I do? I just copied this equation right in here, right? Without this term. Without this term. Okay, and let's see what we can do to simplify it. Let's go another step. This R is going to be big R plus H. Big R plus H, big R plus H. Oops, I put it in the wrong place. It's this one. I want to place it here. Big R plus H, big R plus H. And you're going to see that there will be some simplifications here, right? Okay, that's the V square over R. Let's see if we can, yeah. Can we go another step? Let's see if we have enough space here to go another step. No, it doesn't look like we have another. Let's see, what I can do is erase this one from here, put it here. Yeah. We don't have space, so let's continue here. Like that, right? R plus H outside the parentheses. And now this R plus H is gonna cancel out the other R plus H downstairs. Don't forget, this is the period of the Earth rotation, okay? I'm gonna cancel this one and replace with that one. Okay, T square is gonna go downstairs. When we get, I'm gonna put pi here. Pi is gonna be square, and my 2 is gonna turn into 4. Okay. Okay. What you see right in here is the weight of the person at that height. And what you see right in here is the centrifugal acceleration. Is the centrifugal is the centrifugal force that the astronaut is being subjected to due to the rotation of the tower as it goes around, right? As the Earth rotates, as the tower rotates with the Earth. So it is as though the astronaut is inside a blender, in which the Earth is the blender itself. The further away you are from the center of the Earth, the higher, the higher the centrifugal force is, okay? The higher the centrifugal. And now we have to put all these numbers, all these values here in our spreadsheet to find the exact value of the normal. The normal is going to be a little bit less than 800 newtons, okay? I can tell you right now. Here is around 800 newtons. 400 kilometers is not that much. So G around that height is going to be almost 10 meters per second square. Let's see, I calculated that before. Let's see, at 400 kilometers, let's see. Height of 400 kilometers. G, okay. G is around, I calculated that before. I do not know if you remember, right? We did that here in the class. It's not 9.8, 8.69. So what you are going to see here is a little bit less than 800 newtons. And this one we have to calculate to find out exactly what is the value. And we can do that. Right? Do you remember? We calculate the acceleration of gravity, right, at different heights some time ago. Here you go, at 400 kilometers high, 400,000 meters is 8.69. 8.69 should be maybe 90% of 9.8. Yeah, let's see, maybe even less than 90%. 9.82. Yeah, it's less than 90%. So it looks like maybe 85%. Yeah, it's between 85% and 90%. Okay, between 85% and 90%. And now let's calculate that. We already have the period of rotation of the Earth, right? And then we see if I can get this thing here. Yeah, I gotta write down my formula. Let's see. Normal, okay? Normal in newtons is going to be what? Is going to be the mass of our astronaut. That's 80 kilograms times the acceleration of gravity. What you see, here you go. What you see right in here is mass times acceleration of gravity at height of 400 kilometers. This one here, okay? That's what it is. I can tell you right now. Let me put the mass of my astronaut in kilograms, 80. Okay? So at that height, at 400 kilometers, it's not 800 newtons, it's almost 700, a little bit less than 700 newtons. You see that? 700 newtons, but now we have to subtract the effect of the centrifugal acceleration. And that is going to be what? That's going to be the mass of the astronaut again, times the radius of the Earth, right in here, plus the height. The height we already have here, the 400 kilometers is already here. Close parenthesis, 4 pi square divided by t squared. We already have t here from the previous problem. Divided. Did I put divided? Yes, I put divided. And let's see what we get. We're getting 693. Okay. 600. Let's see. Let's compare that. That doesn't sound right. Let me see. Oh, yeah, that's right. It sounds right. Without the centrifugal force, if the Earth were not to rotate, right, it would be 695. But because the Earth is rotating, is 693 newtons. Okay? So the effect of rotation of the Earth at 400 kilometers high is very small. It's less than 1%. You can see it. From 695 to 693 is 2 out of approximately 700. 2 out of 700. So it's less than 1%. It's less than 0.5% actually. The effect of the Earth rotation is less than 0.5% at that height, right? If you go much higher, the situation changes. And let's get that number. Okay, here you go, 693. And let's just remind you, without the rotation of the Earth, without the effect of the rotation of the Earth, is 695, right? With the effect of the rotation of the Earth, don't forget, we are assuming that everything is in the equator here, right? Including the tower. The tower was built at the equator. I'm assuming that the tower was built at the equator, okay? So, you can do it. It's 2 divided by 693 times 100. Man, this thing is going to be so small. 0.25%, a little bit more than 0.25% difference. So the rotation of the Earth does not affect much the apparent weight of your test subject. Okay, so we can write that down here. Doing the math, we find the following. Doing the math, we find the following. We find the following for a height of 400 kilometers. 1, the weight of our test subject due only to gravity, in other ways, without the effect of the Earth's rotation, is 695 newtons. It is this value because at a height of 400 kilometers, G, right? G is equal to 8.69? No, yeah, 8.69. 8.69 meters per second square. The weight of our test subject due to gravity only, right? Due to gravity only, I'm going to without the effect of the Earth's rotation, with the effect of the Earth's rotation, this number is slightly lower, 693 newtons, okay? Consequently, the Earth's rotation at this height, this rotation at this height represents 0.28% of the final result. Contributes, right? Contributes, not represent, but contributes only 0.28% of the final result. And remember, for the sake of this course, anything less than 10% is negligible. But recall that for the sake of this course, anything less than 10% is negligible. Okay? Then, you gotta repeat that for a height equal to the geostationary, right, position. I can tell you right now, at the geostationary orbit, the normal at the top of the tower will be exactly 0. Okay? So it is at the geostationary orbit where the rotation of the Earth cancels out the weight of the astronaut at that spot. Okay? And you can do this math. Man, we took a long time, huh? I want to stop here on this chapter. Otherwise, we can, there are all sorts of problems that we can play with. And it's already almost 3 minutes, right, to go. Let's see. What I am going to do, I'm not going to do 5.7, okay? We already spent too much time in this chapter. I was expecting to start the other chapter today, but we didn't. I was having too much fun with solving this type of problem, not covered, okay? Will not cover. Apparent weightlessness. Artificial gravity. Here we go. Artificial gravity. The same concepts can be used to find the artificial gravity. I'll let you read on your own how you can rotate a space station to produce artificial gravity. Okay, and it's the same idea. Okay, if you watch science fiction movies, right? People talk about rotating a space station to produce artificial gravity. Something that we have done in the past, but we didn't quite generate artificial gravity. Consider, for instance, a cylindrical structure in space, okay? And that is rotating. Consider a cylindrical, you don't need to know the mass. Here you go. The cylindrical structure is rotating, whatever direction you are, you will be able to produce a centrifugal force that will keep the astronauts glued to the surface, depending on the rotation, okay? Depending on the rotation. And then what would be a rotation that would produce 1G? That's what, and neglect any weight, any gravitational force produced by nearby bodies, okay? So that would be the next one, okay? So consider, here you go, consider a cylindrical space station that rotates along its longitudinal axis. A cylindrical space station of radius r axis, okay? What's going on? Oh gosh, I'm looking. Yeah. What am I doing here? I'm working on the wrong button. This one here. Consider what is its angular velocity, period of rotation, not angular velocity, period of rotation required to produce an acceleration equal to G at the inner shell, right? Of the station, like that. So it's 12:51 right now. Do that at home, see if you can do that, and I will see you Wednesday, right? And don't forget, I also have office hours right now. So see you the day after tomorrow. Thank you for being here.
You.
See you. Let's see here.